basically, I just wanted us to have one opportunity now to go back through everything and see how pieces link together from all the topics that we've covered. I think in the last 2 weeks, we've had a good start at starting to see how the submesoscale and the geostrophic pieces fit in. But I think it's helpful to go back just as a summary of all the topics we've talked together about and touch on a few of the pieces and how they link together again. There are some key themes that I hope will come out of that maybe were not so clear this week as we talked about specific papers. And so all I've done is gone back through the slides from the semester and collected what I thought were key moments from the semester for us to talk about one piece at a time. And I hope you'll be able to see as we go through this why we chose the readings that we chose, why we've had the homework problems that we had, and maybe get a bigger sense of how all the pieces fit together. I think on the first day, if you remember way back when, we talked a lot about all the scales of motion and the different phenomena that occur in the upper ocean, lower atmosphere. And then we have an opportunity now to go back and think about how those all fit together with now the connections to the dynamical theories that support each of those scales. So that's what I wanted to do today, just to give you a sense of where all this goes so that hopefully it'll help retain all the different pieces and maybe make some of the synthetic links across them. Okay, so to the slides. So if you remember, I showed these two funny movies that Ching had put together. This one on the left is an oceanic boundary layer under convection, so cooling and winds. And the one on the right is an oceanic boundary layer under cooling, winds, and waves. And we talked about the qualitative have kind of different directions inducing large-scale slow variability like inertial oscillations, and also the tilting of the Ekman layer. And then in addition, the Langmuir turbulence effect on the right-hand side, where we know now about the Stokes shear force that tends to concentrate the surface convergences into large vertical velocities in the same direction as the wave right-hand side compared to the left-hand side. So we talked a lot about different phenomena in the ocean boundary layer and the atmospheric boundary layer. We went through scaling and dominant balances for a lot of different equation sets. And we talked about the relationship between those scaling and dominant balances in the case of rotating stratified turbulence. We came to think about the turbulence in two different classes. The class of the three-dimensional turbulence, which we talked about most closely through the discussion in Wyngaard, but also a little bit the discussion in Thorpe, where we learned to think about the Kolmogorov metrics, such as the dissipation rate, the second moment budgets, which related the production by buoyancy production or shear production into that three-dimensional turbulence. And we thought about how we could balance the second moments and have things like a production dissipation balance in the energy budget. But we also thought about the turbulent behavior of the systems of quasi-geostrophy and the shallow water equations, and how they look turbulent in that they have a scale-to-scale cascade, even though in those cases the scale-to-scale cascade is quasi-two-dimensional rather than three-dimensional. And so in the quasi-two-dimensional case, we have an inverse energy cascade and a direct entropy or potential entropy cascade, and those have different slopes and different behaviors than we saw in the three-dimensional turbulent case. And so the remainder of the semester, that last 2 weeks where we talked about papers, was trying to give specific examples of particular phenomena and simulations or observations that allowed us to try and link what scales those pieces came in on and how they connected to each other. And so when we go and think about the global ocean, or the global climate system, which has, energy coming in from the sun and being reflected back out, and the heat storage importantly being in the oceans, and the heat transport being partly in the oceans, partly in the atmosphere, and partly in the water cycle away from the equator, we also now can link this concept with an idea that this would lead to a stratified atmosphere, stratified in terms of the potential temperature or virtual temperature, so that ascending air is stabilized, except for maybe in the boundary layer where you might have something more like a neutral or a convective problem, a convective boundary layer. And similarly, the ocean would be stratified because it's warmed at the top. So the ocean is heated at the bottom, which stays largely in the boundary layer, but above the restratification by storms tends to maintain a stably stratified atmosphere, as well as farther aloft in the stratosphere. And that restratification process is through radiation back to space, so of outgoing long wave radiation. And so we put those pieces together, we get a stratified atmosphere, a stratified ocean, and then a relatively unstratified, at least in the vertical, boundary layer in each fluid that's matched together where the exchanges occur. So when we think about the heat transfers coming meridionally in each of those fluids, and the exchanges between the atmosphere and the ocean, so that where the oceans are storing the heat and the atmosphere is transporting the heat, we have a better sense of how that works, and that goes through these boundary layers, those exchanges. Those exchanges are turbulent, and so the way that we came to understand turbulence was through something like a cascade, or we might have a forcing range, an inertial range, where the direct effects of forcing weren't relevant, and so the wave numbers of importance was the wave number at a particular local scale. And so you would think about transfers, not non-local transfers direct from forcing to dissipation, but intermediate scale by scale by scale transfers of things like energy or entropy. These boundary layers that we are talking about, where there is three-dimensional turbulence, are incredibly complicated, both because of the variability of stratification and variability of forcing. And so now when we look at this ocean mix layer that's oscillating back and forth with the seasonal cycle from this climatology of observations, we have a sense of, the transition between the convective conditions, maybe the wind-driven conditions, convective conditions, and stronger winds also in the wintertime hemisphere, stronger waves as well for Langmuir turbulence. And we get a sense of this variation of, from 10 meters near the equator up to hundreds or even 1,000 meters near the poles. One of the challenges when we think about this as far as climate change is, so remember, these are the resolutions, horizontal resolutions of the ocean component of climate models in the different IPCC assessment reports: 6th assessment, 5th, 4th, 3rd, 2nd, 1st. And then here's the highest resolution one and a fit to the highest resolution one in red. And we see that if we're talking about resolving boundary layer turbulence with order of about 1 meter resolution, that's far away. We're not going to be able to, and sorry, this is the year that those simulations were published along the bottom. We're talking about something that is out in the well into the 22nd century for even the finest resolution. So that's how fast computers are getting faster as Moore's law scales. But the median resolution is quite a bit farther out. If we continue to make our Earth system models more complex as we make them higher resolution, we're not going to get to that boundary layer resolving anytime soon. So even though we might be resolving the mesoscale eddies, which we didn't talk a whole lot about, but has a study of mesoscales, something that motivated the study of quasi-geostrophy in particular, the submesoscale and boundary layer turbulence will need to be parametrized and parameterizations require some degree of understanding of how those turbulent flows work. So we don't get to just resolve ourselves out of the problem anytime soon for these smaller scale features. Right, we already talked about that. So when we think about the mesoscale and the submesoscale and the boundary layer, this is a useful idealized simulation to think about. So this is the temperature at the surface. This is the temperature at an intermediate depth below the boundary layer. And then this is a vertical profile down the center of this channel. This channel is kept warm on one side and cold on the other, which keeps a constant thermal wind gradient and so drives a sheared current through this channel. And you can see that it's unstable to mesoscale eddies, which dominate the phenomena at mid-depth. And then those mesoscale eddies have fronts in between them at the surface. And so when we look in cross-section, we can see that that boundary layer stays at about 50 meters persistently as this evolves. So we start by what we can afford more than anything else. And if we take our resolved velocity, our resolved grid scale, and our viscosity, which might actually be a parameterization of smaller scale things, but still an effect in the momentum equation that tends to remove energy and remove entropy, we can construct a grid scale Reynolds number, or a grid scale Peclet number, or a grid scale Rossby number, a grid scale Richardson number, a grid scale Berger number. And these Reynolds, Rossby, Berger, Richardson, Peclet numbers can then be the way that we select the equations of motion that are appropriate to be solved on that particular resolution. So if the Reynolds number is order 1 and the Rossby number is small and the Berger number is order 1 and the Richardson number is large, then we might get the same answer if we use a quasi-geostrophic model as if we use the full Navier-Stokes equations, or at least an asymptotically similar answer. We talked a lot about the fact that those reduced dynamic systems remove gravity waves in the QG case, or remove sound waves in the Boussinesq case. So each time we make an approximation, we do lose some degrees of freedom, some possible classes of motion. But if we're in an asymptotic limit where those classes of motion are not the dominant feature, either at large scales or in the grid scale, then we can safely remove them and expect to have a minimal change to the kinds of macroscopic dynamics of the system, of the resolved parts of the system. A different way to put it is, if we have a grid scale that is at small Rossby number and large Richardson number, then the next scale down, the next thing that's not resolved, is not 3D turbulence. It would still be something that has small Rossby number and large Richardson number. So in a climate model where that's the case, where this Rossby number is small, the Richardson number is large, at the grid scale, the next thing down we should be thinking about parameterizing, the largest unresolved scale is going to be mesoscale, not boundary layer scale. We also have to parameterize the boundary layer because it does things that the mesoscale cannot, like vertical mixing. The amount of energy, the energy density in the mesoscale is not sufficient to overturn density surfaces and cause vertical mixing. The Richardson number, remember we talked about you need to have a Richardson number below a quarter to get gravity wave style overturning, and below 1 to get symmetric instability style overturning. And in either of those cases, you need so if you have a large Richardson number, you just can't do that. Since the Richardson number depends on the vertical scale, but also the shear and the buoyancy gradients, we might think about all of that as being something that we can think about that balance between restratification and mixing as being considering simultaneously a range of unresolved motions. We need the unresolved mesoscale to dominate the lateral transfers, the unresolved submesoscale to dominate the vertical restratification of the boundary layer, and the unresolved 3D turbulence to simulate the vertical mixing of the boundary layer. Each of those comes in at a different Richardson number on a different scale, and a different Rossby number on a different scale. And so we think they have qualitatively different behaviors at those different scales. And so how do we get the equations of motion as a function of scale? Well, the first thing we have to do is we have to get into a rotating coordinate system for our planet so that the Rossby number can be appropriately expressed. And we talked a lot about the Coriolis parameter being this term here, but we also talked about the centrifugal force and how in a geophysical coordinate frame, which is rotating with the local Earth's rotation, the tangent plane is perpendicular to the combined direction of gravity and Coriolis and centrifugal force. And what that means is that the centrifugal force does not appear explicitly in these equations because it's taken up inside of the G factor here in the vertical momentum balance, whichever they're using, the non-hydrostatic or the hydrostatic version of the vertical momentum balance. Similarly, although this isn't as strict of a requirement, this is only considering the Coriolis parameter on the horizontal momentum equations, but there is actually one that goes in the vertical momentum equations, which is the only one that works at the equator. And that's just a matter of geometry. But this set of equations, the so-called F-plane equations, where both gravity and the Coriolis parameter, Coriolis rotation axis are assumed to be in the vertical, is a simpler set where we can still learn a lot. And that's usually the set that we work with. Then we have the conservation of mass, and then the conservation of thermodynamic properties, which might be temperature, potential temperature, or also salinity, or also water vapor. And you put those together, and then you have a closed set. But these equations, even though we have disregarded the frictional and diffusive terms, which means that we're assuming a very large Richardson and very large Reynolds and a very large Peclet number, are still extremely hard to solve. And one of the reasons why is because this compressibility that's persisting in the mass continuity means that we can have sound waves, which limits the time steps because the sound waves are very, very fast. And this part of the equations supports gravity waves. So those might be so fast that we were concerned about it. So if we have a time step that's limited by sound waves or limited by gravity waves, we might want to remove those pieces. The Boussinesq equations assume partial incompressibility. Incompressibility in terms of the mass conservation becomes volume conservation, but we're still allowed to have variations in buoyancy. So even though the volume of these fluid parcels isn't allowed to change in the Boussinesq equations, it is allowed to cause a tendency to rise or sink in the momentum equations depending on your buoyancy relative to your neighbors. The buoyancy can't be determined from the density in the density equation anymore, but it can be determined from the thermodynamic controls on the variations in density, like temperature and salinity, and the equation of state. So the Boussinesq equations remove the ddt, the d rho dt, the difficult part to handle of the compressibility effect, at a cost that we have now filtered out sound waves, and so they're no longer part of this system. Similarly, when we got to large scales, we found that the geostrophic balance was a critical way of organizing the flow that leads to small divergences. It leads to a very simplified vorticity balance on really large scales. And when we put together the smaller divergence and this large scale balance, we came to these two equations, the geostrophic equations, and they have this funny directionality in that the pressure gradient that's relevant is not the one in the same direction as the velocity that it's linked to. There's a perpendicularity between these two. The other truly peculiar thing about these equations is that they are not prognostic. They're diagnostic. If you tell me the pressure field, I can tell you the geostrophic velocity at that same instant. If you tell me the geostrophic velocity, I can tell you the pressure field. What I can't tell you is how it's going to change from these two equations. So these are an incomplete description of the motion. So we need something else, another set of equations, to describe how the geostrophic flow or the pressure field, which are interchangeable, evolves. And that comes through considering the vertical component of the vorticity, and that vertical component of the vorticity, because of this funny directionality, is a curl of the geostrophic velocity field, so it's the Laplacian of this pressure-related stream function. And so when we think about the shallow water equations, which are one step more simple than the Boussinesq equations, in that they are hydrostatic and stacked, and so they don't have overturning. That is another simplification, which is due to flat aspect ratio. And then on top of the shallow water equations, to consider geostrophic flows that were either at the planetary scale, that is small Rossby, a large Berger number. I never can remember whether Berger, this is Berger 1 over Berger. But large scales much bigger than the deformation radius. Then we have a system that looks like this, where now the only prognostic variable is the buoyancy, or alternatively the potential vorticity, or indeed you could think of it as the thickness. These are all the same variable. They're not different in the planetary scale. And once you know either the buoyancy or the potential vorticity or the thickness, you can then make the geopotential, which drives the flow, and then that flow is injected back into the evolution equation, which then causes a change in that underlying scalar field. So we have the idea that from something that had 1, 2, 3 velocities, a buoyancy field, and also a geopotential field, so 5 degrees of freedom, we have now reduced to something that has only one scalar degree of freedom that predicts all the others, this buoyancy or potential vorticity. Similarly, the quasi-geostrophic equations, now not on such large scales, but on the scale of the deformation radius, which implies, and with small Rossby number, implies a large Richardson number. So we have a rapidly rotating, highly stratified system near the deformation radius. Then we get a single QG potential vorticity, which is a single prognostic variable, which through the inversion of this Laplacian can allow us to find the stream function from the potential vorticity, and then it combined with the buoyancy equation evaluated only at the top and bottom, which gives us the boundary conditions on this stream function, in the vertical, we actually can have another closed system. So again, U and V, the velocities, are not independent of this potential vorticity anymore and buoyancy. They're directly inferable from the stream function, which is directly inferable from the potential vorticity, and the buoyancy. So we've collapsed the number of possible kinds of motion, which in practice means we've removed gravity waves from this situation, and we can take much larger time steps in the quasi-geostrophic equations. But still, these equations have interesting classes of motion. They still have eddies and a kind of turbulence. And then the last simplification that we talked about was the Ekman layer, which this is the way that Vallis presents it, really to think about this surface boundary and to think about a stress acting to produce an ageostrophic velocity, a stress divergence producing an ageostrophic velocity. And if this stress were taken to be a linear viscous style stress, then you can solve lots of things. But as we saw in Wyngaard, you don't even have to really make this kind of assumption to really understand the kinds of things that happen. If this is a turbulent stress, you have to either have observations of the turbulent stresses or some kind of scaling law like the Monin-Obukov scaling for it. You can actually make a lot of, you can do a great deal of understanding of the Ekman layer even without this eddy viscosity assumption. So to come back quickly, so now we have a linkage of the large scale dynamics, kind of the background flows. How do we link all of this to turbulence and instabilities? So we have this concept of that comes from Kolmogorov of the forcing range and the dissipation range and an inertial range in between, and through basically Buckingham Pi dimensional analysis, we're able to find things like the dependence of that spectral energy density, power spectrum of energy, on the wave number and the energy cascade rate. And also the scale at which, based on that epsilon, that energy cascade rate and the viscosity, the scale at which dissipation becomes important. In three-dimensional turbulence, we have only energy to think about and only a cascade of energy. And so these are the only scaling laws we get. But in two-dimensional turbulence, or quasi-geostrophic turbulence, we have two different cascades. We have both an energy and an entropy cascade. And so we get two different regimes, one of an inverse energy transfer, which has similar dimensional analysis results to the 3D case, but a different directionality because the vortex merger of two-dimensional motion makes bigger and bigger eddies, more and more energetic eddies, while at the same time making filaments and straining fronts in between those eddies, which causes entropy, a higher derivative of the vorticity, or a higher derivative of the velocity field to cascade in the other direction towards smaller scales. And now the dissipation range is not governed by an energy dissipation, but by an entropy dissipation scale. So this theory has two different ranges of turbulence. Have a conception of an Ekman layer, a boundary layer. In that boundary layer, we might have three-dimensional turbulence. Above it, we might have two-dimensional turbulence, or we might have a combination of two-dimensional and three-dimensional turbulence in the boundary layer. And that's where the submesoscale and boundary layer baroclinicity comes from in both fluids. In the ocean case, we thought about a solar restratifying effect, which might lead to a sheared boundary layer with winds driving overturning. So three-dimensional turbulence that's there because the winds are fighting against the sun. Or we might have no heating or cooling, in which case we'd have a much stronger, more vigorous overturning because it wouldn't have to work against the buoyancy destruction, as Wyngaard calls it, of the sun. Or we know that in the combined submesoscale and boundary layer case, we actually would have restratification coming from lateral gradients. That's something that was not really discussed in Thorpe. That's a newer discovery and not discussed too much in Wyngaard. That's part of the game. But in the Monin-Obukov scaling, we assume that the lateral gradients are negligible, that the scale of heterogeneities of the boundary layer are much, much larger than the scale of all the motions we're worried about. And so in that simple scaling, we come up with that 1D conception of what's important, and the 1D conception just balances the wind stress versus the buoyancy forcing to give us a Monin-Obukov depth, which can be written either this way or this way. So U star cubed over W star cubed, or written like this. And so we have essentially and this scale is the scale that gives you the relative measure of buoyancy and winds. And we'll come back to how that plays out in the atmospheric boundary layer in a second. But the other piece that we came to think about in the ocean case was, of course, waves, which can break and add more mixing, or waves which have a Stokes drift, which can drive Langmuir turbulence, the boundary layer deepening in Ching-Li's paper. And the atmospheric analog also has a Monin-Obukov scale, which now governs how far the convective scale is versus the shear-driven turbulence scale. So we have a transition at somewhere about around 0.1 of the Z over L scale, where you go from the surface layer, where everything is stress-driven, to a convective layer, where everything is convectively driven. This is the case during the daytime when you have an unstable convective boundary layer. And that's, so the Monin-Obukov scale is helpful here in determining which regime you're in. And then whether or not the Monin-Obukov scale is deeper or taller than the top of your mixed layer helps you determine whether you're in training or not at the top of the mixed layer. So these are pieces of the Monin-Obukov scaling coming into this kind of convective boundary layer, which is a little bit like it's the daytime atmospheric boundary layer, a little bit like the nighttime ocean boundary layer, where the surface stresses are causing mixing, and also the waves are causing mixing right at the surface. And then there is in the ocean case, it's a cooling. In the atmospheric case, it's a warming from below, cooling from above, in both cases driving convection throughout the rest of that mixed layer. As the atmosphere is advected over different features, such as cold water, you might have a stable boundary layer growing, which would be a heterogeneity in space, or you might have a nighttime boundary layer that could be made stably stratified by either cooling from above or the entrainment of stratified air from above. So there's a variety of stabilizing and destabilizing mechanisms just in the 1D conception, and where the Monin-Obukov theory is most handy. But when we think about the mesoscale, sub-mesoscale effects, now we're in violation of the Monin-Obukov similarity because we have horizontal gradients, and the horizontal gradients can also lead to restratification as their kinetic energy. And the extraction of potential energy is a restratifying buoyancy production term. Because the sub-mesoscales are small and thus their Rossby number is large, thus they can have big surface convergences and divergences, unlike the relatively quasi-geostrophic modes of the mesoscale, whose vertical velocity is suppressed. The sub-mesoscale actually can have larger vertical velocities, larger vertical fluxes, larger divergences at the surface, and so they do not behave in a quasi-geostrophic way. They behave somewhat like quasi-geostrophy in that potential vorticity is important. The Charney-Stern-Podlosky potential vorticity gradient theory is still relevant to understanding the geostrophic modes of the submesoscale. The negative potential vorticity of the symmetric instability is still important in understanding where the symmetric instabilities occur in the submesoscale. But the submesoscale is not as tightly constrained to have quasi-geostrophic dynamics. It just has potential vorticity as an important indicator of the thermal wind shear from which those modes can grow. So the vertical fluxes can be larger. Quasi-geostrophy is only an approximate theory, very approximate theory for the submesoscale, because the Rossby number is not small. The Rossby number of submesoscale features is order 1 or even order 10 if they're strong. So the vertical fluxes or submesoscale tend to restratify as they extract potential energy. Our energy budget still makes sense. They're still extracting potential energy even though they're doing it using both geostrophic and ageostrophic mechanisms. But the larger and more energetic mesoscale features are actually able to dominate the horizontal fluxes. And they tend to be more of a horizontal stirring process. And so if you want to parameterize horizontal transport, you need to focus on the mesoscale, vertical transport, and vertical restratification. You want to parameterize the submesoscale and the boundary layer turbulence. And in the Hamilton runs, where both the submesoscale and the boundary layer turbulence are both resolved, that's exactly what we see, is that the vertical transport of momentum is dominated by the total is equal to the small scale transport with just a minimal amount of vertical momentum transport by the submesoscale, but the vertical heat transport is balanced between a restratifying submesoscale and a mixing small scale. And that's true whether or not you have the Stokes forces. So Langmuir turbulence behaves very similarly in this regard to non-Langmuir turbulence, and you can see that those pieces are balanced one against the other. It's possible if your wind or wave conditions change that mixing might win for a while, deepening your boundary layer, or it's possible if wind and waves died and convection died, that these might lose for a while and submesoscale restratification would win out and shoal your boundary layer. That's the balance between these two phenomena. And we've already talked about the Charney-Stern-Podolsky instability, but I'll just remind you it's this list of things that had to be required, which is a lot like the Rayleigh-Kuo stability criteria, except it's the three-dimensional quasi-geostrophic theory that works for predicting geostrophic mode instabilities and can be extended into the Langmuir gradient has to change sign, but that the PV itself has to be negative. This is a stronger constraint. This happens only on smaller scales with more intense fronts, and so the symmetric instability tends to be the stronger, faster, smaller, more intense instability, but it's limited to Richardson numbers below 1. And so it very quickly neutralizes itself through its restratification process. The second to last concept that I want to touch on and remind you of is that calculating potential vorticity is complicated within the boundary layer. So potential vorticity is critical for the geostrophic criteria and also for the symmetric criteria, and where it's the key ingredient for the quasi-geostrophy and the way that we connect these large-scale, rapidly rotating, stratified theory together with the three-dimensional turbulence theory. But because of the 5/3 cascade of the three-dimensional turbulence, which is particularly clear here from Abigail's paper, particularly at mid-depth, you can see that it's an isotropic turbulence. U, V, and W are all have the same power spectrum, similar power spectral slope, unlike at large scales where the vertical velocity is totally suppressed and the horizontal velocities are large. Slope from large scales is that the potential vorticity, which is determinable, you would be able to meaningfully describe what the potential vorticity and its variance are, but then it turns around and goes back upward at small scales in this ultraviolet catastrophe that comes from the shallower spectral slope that's expected of Kolmogorov-like isotropic turbulence. So that upward slope means that if we had more resolution, they would just keep going up. And so this isn't fixed by resolution until we hit the Kolmogorov length scale, much, much smaller scales. So this is a problem of all large eddy simulations where we're resolving just the largest of the boundary layer turbulence, not the whole cascade down to viscous scales. And so what that means is that you need to be really careful when you calculate the potential vorticity that's relevant to think about these submesoscale modes, to first filter out these boundary layer terms without taking their derivative and making these spike back upward. And these thinner lines show how you can use a relatively simple filtering technique to make that work, focusing all of your attention on the submesoscales in a filtered potential vorticity dynamics and letting the boundary layer thing come into these equations through their momentum and buoyancy fluxes, not through their potential vorticity fluxes. Okay, last topic that we wanted to discuss was how big are these things in the real world, and how big are the boundary layers, how big are the boundary layer turbulence, how big is the submesoscale turbulence, and this is the surface mixed layer instability, this is the geostrophic branch, this is the bottom mixed layer instability, a geostrophic branch at the bottom of the ocean, and we basically are talking about 1 to 10 kilometers in this case. And remember, we don't understand the boundary layer turbulence well enough to really predict these observed scales perfectly. So we're using a range of different boundary layer mixing schemes. And surface depend more strongly on both season and latitude, having to do with the fact that there's basically the tropics are warmer and then the poles, and that gives you some of this tilt, and the Coriolis parameter is there also changing these scales. But at the bottom you have the Coriolis parameter, but you don't have the seasonality or tropical equator to pole differences in the same way. And so these are more just a boundary layer that's persistent across all latitudes, even though there is a small amount of variation. These scales are much smaller and less sensitive to latitude, less sensitive to season at the bottom. And what does this mean if we project our resolutions forward? Well, here's the high resolution run that we use to diagnose those boundary layer depths, and it's not yet into resolving the winter time. It's nearly resolving half of the winter subsurface mixed layer eddies, but is still quite a ways, about a factor of 3 away from resolving the summer surface mixed layer eddies, and quite far, more than an order of magnitude away from resolving the bottom mixed layer eddies at that resolution of 2 kilometers. The symmetric instabilities are smaller still. They require these very intense fronts. So even though they're partially or barely resolved, 10 times smaller is not going to be resolved at all. And so the resolved, and that's the scalar model. So we don't really understand what they do on a global scale to this whole stratification and how much of a change they make to the boundary layer depth. So the understanding the role of the submesoscale is still ongoing in this regard. Okay, so that's what we have talked about this semester. We talked about a lot of things that occur in the ocean boundary layer and the atmospheric boundary layer. Talked about the dominant balances, particularly geostrophy, Ekman, and then the dominant closed, distinguished limit closed systems like the Boussinesq system, the shallow water equations, quasi-geostrophic equations, planetary geostrophic equations. And then we talked about rotating stratified turbulence and instabilities of the OBL, the ABL, and the larger scale submesoscales. So that's what we've done. I hope that everybody has enjoyed this semester as much as you can and has learned a lot. This is a surprisingly challenging semester to do all this in, and I really appreciate all of you plugging away till the end and still listening and thinking about this, working on the homeworks. And I hope that your final paper feels like a kind of like expansion of your capabilities, grasping and pulling together threads that you hardly even knew existed at the beginning of this semester into a story that really makes sense and makes you feel like you've gotten somewhere. So with that, I'm going to stop the recording. And are there any questions on the final project?